Hi everyone, it's time for us to all work on the small shell assignment now. And this assignment is pretty infamous in the program. I'm sure you've already heard of it before taking this class, for being one of the hardest and most time-consuming assignments in the program. What I often hear from students after they complete the assignment was that it wasn't nearly as hard as they had anticipated, but it took a lot more time than they were expecting. The other thing that I hear from students pretty frequently is that they often don't feel like they're making significant progress or like the assignment is really coming together until they're very close to the end. And that feeling can be pretty demoralizing, and it can be difficult to stay motivated to push through all of the different requirements that this assignment has. My recommendation would be to break the assignment down into smaller, discrete parts or goals and work towards each of those goals individually. This might help you maintain that motivation throughout the assignment. So in this assignment, we have 8 major tasks that we're going to be working on. The first task is relatively simple. We'll be printing an input prompt for an interactive terminal interface. The second part is to parse the command line of input into words and then identify certain words as tokens or operators. We'll be implementing parameter expansion, so we'll recognize 3 special shell parameters. We'll also recognize generic named parameters. We'll then implement 2 shell built-in commands, the exit and cd command. And then for any other commands, we'll execute them as non-built-in external commands using the exec function, which you'll be learning about in the upcoming modules. For the non-built-in commands, we'll also be implementing redirection using these 3 operators here. And we'll be implementing the ampersand background operator to run commands in the background. We'll also be implementing custom behavior for the sigint and sigtstop signals. The basic structure of this program should be an infinite loop. And in that loop, you're going to perform these 6 major tasks. Now, they might not appear in exactly the order or location shown here, but this is the general layout of the program. The loop will be exited when the built-in exit command is executed or when the end of input is reached. When the end of input is reached, your program interprets that as if an exit command had been issued. There are 2 ways that small shell will be invoked. One is with no arguments, in which case it will just read its commands from standard input. If it's instead provided with 1 argument, it will open that file and read commands from there instead. These will be referred to as interactive and non-interactive mode in the rest of the specification. The reason that we have it this way is because in interactive mode, any executed child process will inherit the file descriptors that small shell has open at the time that the child process is forked. And because of this, we run into issues with child processes that consume input on standard in, interfering with the commands that we're trying to pass into small shell during testing. By having small shell open a separate file to read commands from, we can ensure that the input that external commands reads from is separate from the commands that small shell is reading from and executing. So this behavior right here is absolutely critical for your assignment to receive any credit during testing. So in non-interactive mode, small shell will open its file or script with the close on exec flag, and we'll talk about this more in a minute. This makes it so that child processes won't inherit that open file descriptor, so they won't be able to access that file. they'll only see the standard in, standard out, and standard error file descriptors that Smallsh inherited when it was first invoked itself. Okay. Throughout the specification, we'll also explicitly mention certain types of errors. When an explicitly mentioned error occurs, the program will print a diagnostic message, and then it will update the value of the question mark or status special shell variable to a non-zero value to indicate that the previous command failed. Further processing of the current command line will stop, and you'll return to step 1, which is right here. Any other errors or edge cases are unspecified and left up to you as the programmer to decide what to do. I would recommend in general that most errors you can simply exit the program with a non-zero exit status and print an error indicating what went wrong. This is really important to do because it ensures that your program doesn't have a lot of undefined behaviors or unexplained crashes or bugs, which can be very difficult to figure out if they end up impacting your program. So throughout the specification, I've highlighted some text in purple here, which these are comments and don't necessarily specify any requirements for your program. So it can help you differentiate what you really need to pay attention to, especially when you're going back through the assignment at the end to make sure that your program meets all of the requirements. In the first step of your program, you're going to be retrieving input from the user. Now, before you do that, you might have some background processes that are running from a previously run command. And so at this point, right before printing out a prompt and reading a line of input, you'll be checking for any of those background processes to see if they exited. If they did, you'll print out informative information about their exit status and whether they were signaled or exited. If a child process was stopped, you'll print out a diagnostic message about that, and then you'll send a signal to it to tell it to continue running in the background. Now, this behavior isn't necessary until you've actually implemented background process functionality. And that's one of the last things that you'll do in the program. So we're just going to skip over this for now. In the interactive mode where Smallsh is reading from standard in, you'll also print a prompt by expanding the PS1 parameter or shell variable. If you look in the section below, it explains how parameter expansion is supposed to work. Otherwise, nothing shall be printed. So for now, let's not worry about interactive mode. These are all things that you can add in later to the program to enable this functionality. We'll assume a default of Smallsh reading from a file instead in non-interactive mode. So the first actual step that we want to implement is reading a line of input. And this is pretty straightforward. In interactive mode, it reads from standard input. And in non-interactive mode, it reads from the specified script file. And this is pretty simple. It's very similar to what we did in the base 64 assignment by having a open file stream and setting a variable called input or something along those lines to either standard in or the open file, and then reading from there. There's some additional tasks that will need to be implemented for interactive mode if reading is interrupted by a signal. So we'll not worry about that right now because that can be done later. After reading a line of input, the input will be split into words. The words are delimited by whitespace characters, including new line. So when you read a line of input using getLine, for example, the last character in that string will be a new line character. So we'll assume that that new line character is also a delimiter, and therefore it will probably be removed during this step because it counts as whitespace. If a backslash appears anywhere in the input, it's removed from the input line and the next character is included in the current word, even if it's a whitespace character. So this is just a simple backslash escaping mechanism. Notice that this doesn't preserve that escaped trait in any future steps, since the backslash is actually going to be removed entirely from the line. So for example, you cannot backslash escape a $ to avoid expanding a parameter later on or anything like that. It's just to allow white space in the input, which is really important for testing purposes, because there are a lot of things we want to test that require spaces within arguments. And this is probably the easiest way to go about doing that. If a hash or # comment character is encountered at the beginning of a new word, that character and any characters following it will be removed from the input. So we'll also allow comments in the input as the trailing component of a line. The program will support a minimum of 512 individual words in the input. So if the input contains more than 512 words, the behavior of the program is undefined. Of course, you can write your program to support more than 512 words if you want, but the minimum is 512. I will note that we're not going to explicitly test that your program supports this limit, but it should support at least a large number of arguments for testing purposes. After you have split the input into words, you're going to expand each word. So expansion is where we identify within a word certain sequences of special tokens or special characters which indicate a shell variable is to be expanded. That sequence will then be replaced with the corresponding variable. So the double $ or $ variable will be replaced with the process ID of the small shell process. So this is the same way bash works. For example, if I echo out the double $ variable, 76740 is the process ID of the current running bash process that this command was entered into. The question mark shell special variable will be replaced with the exit status of the last foreground command. So for example, if I print it out now, the last foreground command exited with a status of 0. Let's say we run the false command, which just exits with a value of 1. And then if we echo out that variable again, the result is 1. Your shell should behave exactly the same as this. We'll also have the exclamation mark shell special variable, which will be replaced with the process ID of the most recent background process. So you'll track the process ID of the most recently executed background process, and you'll report that back when the shell variable is expanded. Bash also has this functionality. So by default, this parameter expands to an empty string if no background process has been run. If we run a process in the background and then we echo out that variable, it will print out that process's ID. Finally, it will support expansion of generic parameters using the following notation, which is also exactly how bash works. So this echoes out the contents of the path environment variable here. Now bash also does support a bracketless notation for variable names that are unambiguous. But we won't be supporting that. We'll only support this format here. And you'll be expanding the corresponding environment variable. So we won't be tracking any internal shell variables the way that bash can. We'll only be tracking or expanding environment variables that were set when small shell was invoked. And you should read about the getEnv function to learn how to query those environment variables. In any situation where an expanded environment variable is unset, it should be expanded as an empty string, and this is not an error. This also includes PS1. So bash does the same thing. If we wanted to expand a variable that doesn't exist, there's no error, it's simply an empty string. This also applies to the PS1 environment variable that we mentioned earlier when you go to print the prompt. So if PS1 is unset, it's not an error, it just is empty. So the question mark parameter defaults to 0. The exclamation parameter defaults to an empty string. Expansion is not recursive and is performed in a single forward pass through each word. So for example, if a variable is expanded and that variable contains a $, that $, will not take part in any other expansions, so you can't have recursive expansion. You also can't have part of an expansion form part of another symbol or a token that would be recognized as a variable name. Since this is not the primary purpose of the assignment, we're really focusing on process concepts here. I've provided some sample code that accomplishes this task for you. After splitting into words, you need to parse the words syntactically into tokens. So this means you're going to look through the list of words and you're going to identify ones that have special meaning. If the last word in the list is an ampersand, it's interpreted as the background operator, which means that the process is to be run in the background. If you come across any of these three words, the redirection operators, you'll interpret them as those tokens as well. The word immediately following these redirection operators is also considered the redirection operator file name, and will be recognized as a token as well. I'll probably add a note to the assignment here about that. So if at this point no command word is present, and that's not including any of these tokens, Smallsh will silently return to step 1 and print a new prompt message. This is not an error, and you will not change the status variable or print any diagnostic about this. This is the same way bash works, where if there is nothing to do, it simply prints a new prompt. At this point, we'll handle built-in and external commands. If the command to be executed is exit or cd, you'll execute the following built-in procedures. We will not test redirection or background operators from step 4 with built-in commands. So you will never have exit with a redirection or in the background, and the same goes for the cd command. You may implement whatever behavior you want in the event that those tokens appear. You can just treat them as regular arguments. You can remove them from the arguments. You can have your program exit, whatever you want. The exit built-in will take one argument. If an argument is not provided, it's implied to be the expansion of the status special variable from the last foreground command. If more than one argument is provided, or if the argument is not an integer, it will be an error, so you print a diagnostic message and you return to prompt for the next command. Smallsh will exit with the specified value, or if there was none, it will exit with the status of the last foreground command. It does not need to wait on any child processes, and it can exit immediately. The cd built-in takes one argument. If that argument is not provided, it defaults to the expansion of the home environment variable. So cd with no arguments is equivalent to cd home. This should have curly braces around it, by the way. If more than one argument is provided, it will be an error. It's also an error if the operation fails. So Smallsh will change its current working directory to the specified path. If that path does not exist, or it does not have permission, or another error occurs, you'll print a diagnostic message and return to the prompt. Then we have non-built-in commands. So any other commands will be executed through this pathway as an external command to be run, or an external executable. If the command name does not include a slash, it will be searched for in the system's path environment variable. Otherwise, it will be interpreted as a path to a program. Now, some students have tried to implement this functionality themselves, but you really need to read the exec VP documentation, because the system can handle this for you. There's an implied fork in this process. If it fails, it will be an error, and you will return to the prompt after printing a diagnostic message. In the child, we have a slightly modified error condition behavior. So after a fork, if in the child process, if an error occurs, the child will print an informative error message to standard error, and it will exit with a non-zero exit status. All signals will be reset to their original dispositions when Smallsh was invoked. So in interactive mode, we'll have some extra signal handling functionality, and you want to make sure that you reset those signals before executing the child process so that it responds to them properly. Then you'll perform redirections within the child. You'll scan the list of words left to right for redirection operators. If a redirection operator is found, the word following it will be interpreted as a path to a file. If there is no following word, or if redirection fails for any reason, it will be an error. So the child will print a diagnostic message and exit. The input redirection operator specifies to read the specified file for reading on standard in. If the file does not exist or cannot be opened, it's an error. The output redirection operator instructs the program to open the specified file on standard out. If that file does not exist, it will be created with permissions 777. Make sure to include the 0 to specify that this is an octal number in C. The file will also be truncated if it already exists. Then we have the append operator, which works similarly, except the file is not truncated and it's open for appending. Finally, the redirection operators and their file name arguments, along with the ampersand background operator, are removed from the list of arguments prior to executing the non-built-in command. If the child process fails to exec, it will be an error as well. So make sure to handle that case. That's a common cause of bugs, and can immediately fork bomb by sending Smallsh into an infinite loop where it's forking child processes that become parent shells by accident. So make sure after a call to exec that you have some functionality to exit unconditionally in the child process if the exec fails. After executing a foreground command, Smallsh should wait on that command. If the background operator was not present, Smallsh will wait on the foreground command. It will update the status shell variable to the exit status of the waited for command. If the waited for command is terminated by a signal, it will instead be set to the value of that signal plus 128, which is also the same behavior that the shell uses. In case you're wondering, this does mean that if a program exits with a status that is greater than or equal to 128, it's very difficult to differentiate whether that program was terminated by a signal or whether it exited normally. And for this reason, most programs only use exit values in the range 0 to 127. Or actually 128, because signal number 0 does not kill processes. If the foreground child process is stopped rather than exited or signaled, Smallsh will send it a sig continue signal and print the following message to standard error: child process stopped, continuing, with the process ID here. The shell variable for the most recent background process will be updated to the PID of the child process as if it had been originally executed as a background command. Smallsh will then not block on that process, and it will continue to run that process in the background. Any other child state changes should be ignored. Otherwise, the child process runs in the background. So this was all if the ampersand operator was not present. If it was present, then the child process runs in the background. The parent Smallsh process does not wait on it at this point. And I just want to point out that this is the default behavior. If you fork a process, it's already running on its own, and it runs in the background unless Smallsh stops and waits for it to finish. The only thing that you do in this case is set the background process ID variable to the PID of that process. Finally, we have some additional steps that you have to perform related to signal handling, only in interactive mode. In non-interactive mode, Smallsh will not handle these signals in any special way. So this is also something that you can ignore until you get to implementing the interactive mode functionality. Down below, I've provided some guidance and some example code for some of the string manipulation that you'll need to do. And I've talked about how you can easily test your program. And then you'll be including a makefile and submitting as many source files as you want up to grade scope. But you will need to include a makefile with this assignment to ensure that your program is compiled correctly. And that way we can account for all the variations in how students attempt to write the program. Your program will be graded out of 180 points, and these are the rubric items that we'll be testing. In general, we'll be testing things in an attempt not to break your program. So for example, these tests here will be relatively simple. You do need to expand these variables within words and as standalone words. With multiple parameters and multiple words, we will attempt to break your program. The built-in commands will be tested with both the no arguments and single argument and multiple arguments cases. The redirection operators will be tested individually and then all together. With the multiple redirection operators in one command, we will attempt to break your program. One thing I want to point out is that if there is no word after a redirection operator, then the behavior of the program is not defined, and you can just exit. We won't test that particular behavior, so we'll always provide a file name. We also won't provide an ampersand as a file name. So for example, if you look at the specification, technically this would specify that as you read from left to right, you encounter the redirection operator and then an ampersand, which would be interpreted as a file name. We won't test this because it's a particularly nasty edge case. One We'll also test the background command operator in background commands. So we'll test if the command actually does run in the background, which means you return to a prompt and allow additional commands to be executed immediately, even if the background process is blocked or still executing. Once the background process exits, it should report the exit status correctly. If it's signaled, it should report the signaled status of the process correctly after it exits. Then we'll be testing whether a SIG continue signal is sent to a stopped background process, and also if it's sent to a stopped foreground process. So both of these behaviors happen in different places in the program, but they're basically the same behavior. With this one, we'll also be testing to ensure that the background process ID parameter was set correctly. I should note that with these variable expansion tests, you have to have actually implemented the appropriate behavior. So for example, you have to have background processes working in order for these points to be awarded. You have to be able to execute foreground commands for these points to be awarded. Then finally, we'll test interactive mode. Test to see if you print the PS1 prompt. We'll test to see if you correctly ignore the SIG T-stop signal. We'll test to see if you reset signals in the child processes. Now, in order to get points for this, of course, you have to pass these two tests to show that you've implemented the signal handling functionality in the first place. We'll then see if you correctly ignore the SIG int when not blocked and reading for input. And we'll test to see if you correctly respond to SIG int when it interrupts input reading. So while sitting at the command prompt, for example, if you hit Control-C to send a SIG int to the process, it causes a new prompt to be printed. Okay. But in this here, you can see that the signal behavior of this was reset for the sleep command, so that this instead caused the sleep command to exit. And it was also ignored during this time by the parent shell. If it wasn't ignored, we would have seen two prompts printed out here, one for sleep exiting and one for the Control-C signal being received by the shell. Okay. So this is the last thing you should implement in your program, probably. This is the second to last thing. And basically everything here is shown in the order that you should implement it. And I expect most of you to get at least comments and variable expansion right out the gate, especially because the provided code handles this for you. The built-in commands should be relatively straightforward. And this is the order that I do recommend going through implementing the program. So let's go ahead and start with a little bit of an example. Now, one thing that you'll need to do at the very top of your program is define the POSIX C source 2008-09L. So this is a number, so the L is long. It means that this is a long int. 2008-09 is a date, so it's the year 2008, the month is September, and that is when the POSIX 2008 standard was officially published. So this number here is checked by various header files to determine whether to expose certain features or not. If those features predate this POSIX standard, then they will be hidden in the final program. And you'll get all kinds of compilation errors about things not being defined when you go to use signals and things like that. You'll probably also want to use the additional extensions provided by the GNU source macro. So for this one, you don't set it to anything, you just define it, and its existence is enough to expose those features. And this gives you access to a lot of additional helpful utility functions and convenience functions that you wouldn't otherwise have. Most of them you could implement yourself very easily. They're usually no more than a couple of lines of code, but this kind of speeds things up and avoids having to reinvent the wheel. So of course we'll have some pretty standard includes here, so we'll probably need standard library.h, probably need standard IO, and a few more here. We'll need the uni standard .h at some point, and there will probably be a few more as you go through implementing the assignment. So we'll have a main function, and just like with the base 64, you'll have some kind of input variable. Oops. Okay, so this is a pretty standard program preamble. So we are setting this input variable to standard in by default. I like to use a second variable to track the input file name. So by default, I set it to something like standard in parentheses. And then later when I need to report read errors and things like that, I can report whether it came from standard in or whether it came from a particular file that we opened at some point. So this is kind of a nice little flourish to have. And then here I set it to argv1 if we are going to read from a file. We'll use fopen, and we will use the extension of the e parameter. So if you just look at the C standards, it's not part of it. So if we look here, we have read, read and write, read and write, etc., append. But then down below, there are additional extensions available with the GNU C library, glibc, and one of them is the E character, which indicates that we should use the clo exec flag, so the close on exec flag when opening the file. Okay, so that handles this part of the specification right here. Now, if you didn't have that extension, it would be a little bit annoying. You'd have to say something like int fd equals open, input fn. The flags would be o read only, o exec, something like this. And then, of course, check if fd is less than 0, error, blah, blah, blah. And then you would have to say input equals fd open. Something along those lines. So it's just a little bit more verbose. So that E takes care of that for you and allows you to open with the clo exec flag. Okay, otherwise if there's too many arguments, we exit with an error, and that handles that behavior pretty easily for us. Now we're just going to have an infinite loop for the rest of the program. Right off the bat, we probably want a prompt label, since at several points we'll need to return to this location unconditionally. You can always use the continue keyword, which will return to the beginning of the for loop. But there are places where you might be within a nested loop or something, and you want to go back to the prompt without having to have some kind of sentinel variable. So this is where go-tos are really useful. Now you've probably heard not to use go-tos. Whoever told you that probably isn't a C programmer and doesn't really know much about programming at this level. We use go-tos a lot in C programming. They're pretty much necessary for proper resource allocation and deallocation. The only alternative is extremely deeply nested if statements or a lot of functions that exist only to encapsulate failure. And both of those things are hard to maintain and hard to follow, whereas a descriptive label can be really helpful when they're used in a conscious and meaningful way. Okay. So pretty much the first thing we're going to need to do, if we look here, I'm going to add in some notes for to-dos. So we'll have that behavior that we need to handle later. Then we'll say to-do, we have the prompt. Okay. Now there are a lot of ways to handle the interactive mode, but I don't want to make this a super complicated part of the program for you either. But we do need to be able to turn off certain things for testing. And one thing we don't want is the prompt getting in the way of testing your program's output. So the easiest way to handle this, you might be tempted to use a separate variable to track is, something like is interactive. So you might put something up here. Set it to 1, and then here set it to 0. Something along these lines. But there's actually a much easier way to do this. If input is standard in, well then we're interactive. Otherwise it's a file. So you can fill in the rest of the code there. Then we have reading a line of input. So this is the first thing that you'll want to do. You'll be calling getLine for this. Oops. Right here. You should read the man page for this, and you'll notice that in order to access getLine, you would have needed the POSIX source variable or macro to be greater than or equal to 2008-09L. So this was added to the 2008 standards. And so if you didn't have this line, getLine wouldn't work. Okay. Now actually it would work because you would still be linking against the standard C library after compiling your program, but the problem would be that you wouldn't have an exposed declaration for it. So you would have to, you would have to manually provide it in your program rather than being able to pull it in through including standard.io.h. Okay. So the way this works is you pass in a line. I'll talk about this in just a sec. So it's going to look something like this, okay? And then something along these lines, or a line length, okay? So, you really need to read the man page for this, but basically what we're doing is we are passing in a pointer, so the address of our line pointer of our string here. So getLine will allocate space for that line that it's reading in, and then it will update this pointer to point at that memory location, which is why we're passing in the address of the line pointer rather than line itself. If we just did this, it wouldn't be able to update our pointer for us. Then we pass in a reference to a size t variable that tracks the size of the buffer that getLine allocates. So getLine will set this to a value, which is the size of the line buffer. Now that value might be larger than the actual number of characters that are read. To you, that value is essentially meaningless. It's used by getLine in subsequent calls with the same input, with the same arguments to decide whether it needs to reallocate that space for a longer line or a shorter line, or whether it can continue to use the buffer that's already available. So for example, we don't have to set this to null. We could set this to something like malloc, 512 bytes, and then we could set this to 512 going into the call to getLine. And it would update these if it needed to reallocate line. And of course, it has the behavior that if line is null, then it will allocate it. It will do the first allocation for you as well. So the variable that you actually want to be looking at, or the result of this, is the return value, which is the length of the line that was actually read. So n is greater than or equal to the return value, but it doesn't necessarily tell you anything useful. Very common mistake that students make. Now, of course, if this is negative, it's an error. You can just print out the file name if you want, or something along those lines. So now we have a line of input. Now there's one thing I want to point out. It's that every time through this loop here, these two variables will get recreated. So every time an automatic variable is declared in a loop, each iteration through that loop declares a new variable with the same name as the previous one, which was destroyed at the end of the loop iteration. So at this point here, these three variables will cease to exist. And then coming back through the loop, they will be redeclared. Now, this is a very common source of bugs in students' programs because they either think that this only happens once and so this won't get reset to null, or they do something even worse like this, where they don't initialize it initially, but then they, something if first time line equals 0 or something along those lines, okay? And the reason that this can cause a lot of bugs is because it either appears that your variables are being reset to their initial values, which is really confusing if that's not what you're expecting, or in a case like what I have right here, it appears that the variables are actually retaining their values across iterations of the same loop. And the reason that happens is pretty straightforward. It's because when these variables are declared, they are pushed onto the stack in the order that they appear. So when you exit a loop, you're popping all of those things off of the stack, and then when you go back through through the loop, you're probably pushing them all back on in the same exact order that they were just in. And since the stack isn't zeroed out when a variable is popped off, it picks up the value from the last time that variable was pushed onto the stack. But it only does that because of undefined behavior, and of course that memory could contain any value at that point. So it's really important that these actually go outside of the loop and get declared out here. And of course, you need to initialize line at least to null. You should always initialize your variables in their declarations if you can. And this ensures that these two variables will retain their value across iterations of the for loop, so that getLine doesn't cause problems for you. Okay, so now that you have a line of input, you need to split this into words, and this is where if you want to do this yourself, you're more than welcome to. But I've provided some code for you, which is right here. Okay. So you can go ahead and copy this code. And I will say I wrote this code in about half an hour. So if there are any bugs, please post something up to Ed, and we'll all update it and be able to avoid those issues. But I have tested it, and it seems to be working properly. So for the isSpace function, we'll need to add an include for the C-type header, which is a bunch of functions to their functions of the form is XYZ, and they return a Boolean value of whether something is or isn't a space or a punctuation or a number, etc. And basically this function will take a line of input, and it will allocate it will identify words, and then it will allocate space for each word and store them in, or store pointers to those words in this words array here. And you can see that, oops, we have an extra parenthesis there. And you can see that this is set to 512 elements because that was the requirement for the program to support a minimum of 512 words. So we can go ahead and we'll move the declarations for these up here. So that we can use them in our main function. And then we can just go ahead and call word split. Oh, one other thing I would probably change is to change this return value to size D. It doesn't really matter because an integer can easily hold all of the indices of this array, and it's probably actually slightly faster. But if you want this to be a generic function, and you want this to be something like this, then you'd probably want to make sure that this is size t instead of an integer in case max words is some ridiculously large value. And this is a really common way to have sort of hard-coded compile time constants in a program that are easy to change. So you have an if not defined max words, then define it to 512. So you pick a default value. But this allows at compile time to specify or override the max words macro with a different value if desired. And what else should we test here? Probably if probably don't want to continue to attempt to read words if our word index is past the bounds of our array. So we might want to have a check there as well. Although 512 words, like I said, we're not really going to test this. But there are definitely things you could do to make this function here a little bit more robust. Another thing is realloc can technically fail. So the more proper way to do this would be to do something like this. So reallocs should usually be a three-step process where you store the result in a temporary variable. You make sure it wasn't null, which would have been an error, and then you set your pointer to that value. So don't take this function that I provided as some kind of gospel. It's just there to help you get started, and should be good enough for most of you to complete your program. You may even want to write your own word splitting function as an exercise at some point, and this will give you a decent example of how to go about doing that. Like I said, this is just something I wrote pretty quickly in order to provide some assistance on the program. So let's go ahead and do that. I guess we're size t now, so size t n words. Let's word split. And we'll split our line. And then we can go ahead and print those out if we want. And compile. And we can see that it is now splitting our words properly. So we could say like hello world. And you can see how backslash escaping is implemented to allow white space to be escaped. You can have comments, and so on and so forth.